Welcome. In this video, we are going to make the claim that we are moving at twice the speed of light. We will use data from today's precision cosmology and the balloon model or analogy of cosmology, and we will find some striking results. You may be familiar with the balloon analogy of the expanding universe, often used to demonstrate how galaxies can move apart from one another. Place dots on a balloon, and as you inflate the balloon, the dots move further and further apart as the balloon gets larger in diameter. The balloon analogy goes back to at least Arthur Eddington. And this is a quote from his book, The Expanding Universe, and this is the 1952 edition. For a model of the universe, let us represent spherical space by a rubber balloon. Our three dimensions of length, breadth, and thickness ought to all lie in the skin of the balloon, but there is only room for two, so the model will have to sacrifice one of them. That does not matter seriously. Imagine the galaxies to be embedded in the rubber. Now let the balloon be steadily inflated. That's the expanding universe. Notice Eddington made no reference to a fourth dimension in that statement. He says, our three dimensions of length, breadth, and thickness ought all to lie in the skin of the balloon, but there is only room for two, so the model will have to sacrifice one of them. It appears Eddington did not view his balloon analogy as a 4D model. We will add the concept of the fourth dimension to the balloon model. The dimension we will sacrifice is the thickness. In place of that, we have the fourth dimension. The dimension running from the center of the balloon to the surface, through the surface, that's our thickness, and beyond. In the balloon analogy is the fourth dimension. The three dimensions of our 3D space are reduced to two, which lie on the surface of the balloon. Understanding a four-dimensional sphere is tough to do, so we will use a couple of analogies first. Let us first look at a line. A line is one-dimensional, and the distance from the center to the edge could be viewed as a radius. If we take our line, we can curve it around and make a circle. A circle is two-dimensional, and a circle has its own radius. The surface of the circle is one-dimensional. It's the line. We're going to step this up one dimension. This represents, or is, a flat piece of paper measured and cut to be a circle. This is two-dimensional. And the size of the circle is equal to the surface area of the softball here, which is three-dimensional. Now if we take our piece of paper, our 2D surface here, from the center to the edge of it we have a radius. And taking the paper, or the 2D area, and curving it around to cover the surface of a softball, we find that the ball, now it's 3D, and it has a radius going from the center of the ball, because we're not going to cut this ball in half, but for going from the center of the ball to the edge is the radius of that sphere. We've seen that we can take a one-dimensional line and curve it to form a two-dimensional circle, the surface of the circle being one dimension less. We take a 2D circle, a flat area, we can curve it around to form a 3D sphere, and the surface of the sphere is one dimension less. And from the previous two examples, let us look at what we get if we curve a 3D space around to form the surface volume of a 4D sphere. So we'll take a 3D sphere, and we're talking about the volume, that's the inner space of the sphere, and we curve it around to create a 4D sphere. What do we get? Well, it might be a cheap way out, but we can't imagine what a 4D sphere would look like. It's beyond our ability. So we're forced to use other methods to explore it. And to do this, we're going to use the balloon analogy concept. So we're going to take our 3D sphere, and our focus is on the volume, the inner volume, the volume. If we curve it around, as we're going to show over here, we have a problem because this is two-dimensional. We're going to preserve the fourth dimension because that's the interest for us. And the surface, instead of a one-dimensional line, we're going to have it represented as 3 dimensions. So 3D are hidden in this one dimension. So in our two-dimensional representation of our four-dimensional sphere, we have to sacrifice 2 dimensions. The surface is 3-dimensional, and that surface represents the universe. So the universe is the 3-dimensional surface volume of our 4-dimensional sphere. The term we're going to use for the entire structure is hyperverse. So we will refer to this entire thing here as the hyperverse, and the surface as the universe. So again, the surface of the hyperverse is the universe. And importantly, the center of the hyperverse is hollow. Now, let us ask, if the universe is the surface volume of a 4D sphere, how big is it? How big is the hyperverse? And we can solve this using standard geometry equations. So what we want to do is take a 3D sphere and look at the volume of that sphere and find a 4D sphere whose surface volume, which is also 3D, equals that of our 3-dimensional sphere. The equation for the volume of a 3D sphere is 4/3 times pi times its radius cubed. And r sub o stands for the radius of the observable universe, the distance from the center to the edge. Now, from our point of view, we reside in the center here, because every direction we look, no matter which way we look, we see as far as we can see. And so what we see around us is a sphere of space. Coming over to the right, and our 4-dimensional sphere, the universe being the surface of it, we have a different radius we're going to deal with. That's going to be r sub h, radius of the hyperverse. The equation for the surface volume, the area in blue, our universe, if it were a surface of a 4D sphere, is 2 pi squared times the radius cubed. And again, this is the radius of the hyperverse versus this other radius, which is the radius of the observable universe, because we've curved the space around. So we're going to set the two volumes equal. The volume of 3D space as we see it, with us being in the center looking in every direction that we can, compared to the surface volume of a 4D sphere. So we set our 3D sphere volume equal to the surface volume of our 4D sphere. So now we can solve for the radius of the hyperverse. And doing the algebra, we find that the radius of the hyperverse, which is the radius of our 4-dimensional sphere, is equal to the radius of the observable universe, which is the radius of the space that we live in, times the cube root of 2 divided by 3 times pi. So how big is the radius of the observable universe? That is, how big is r sub o? Estimates place that distance at about 46 to 46.5 billion light years. So we'll take the equation we just developed where the radius of the hyperverse is equal to r sub o times this factor. And for r sub o, let's stick in the midpoint between 46 and 46.5. We'll put in 46.25 billion light years. And the result is 27.58659 billion light years. The universe is about 13.8 billion years old. If we divide the size of the radius of the hyperverse, r sub h, by the age of the universe, we can find out how fast it has been expanding. The radius is 27.58659 billion light years. The age is 13.8 billion years. And doing the division gives us 1.999. And that is 1.999 light years per year. Despite the current precision of cosmology, measurements are still subject to some error and variation. 1.999, for example, suggests the true answer is 2. If the universe were the surface volume of a hypersphere, then it is expanding into the fourth dimension at twice the speed of light. Is this just a coincidence? Does it have meaning? And if you are wondering or saying to yourself, but nothing can move faster than the speed of light, that statement applies to motion within the universe. Let us look at another calculation we can make from this model. Again, if the universe was the surface volume of a hyperverse, we can ask, how fast is the circumference expanding? This too is easy to answer. We will use just a little math, as some viewers may want to see this. The rate of change of the circumference of a circle is directly related to the rate of change of its radius. And the relationship is 2 pi. That is, delta c sub h over delta r sub h is 2 pi. Now we know that delta r sub h, the rate of change of the radius, is 2 times the speed of light. So we can rearrange this equation here, and we find that delta c is equal to 2 pi times delta r, which is 2c. So delta c is equal to 2 pi times 2c. Now we can ask the big question. What is the rate of growth of the circumference per point of the circumference? To do this, we divide the previous value by the circumference of the hyperverse. So our delta c sub h divided by the circumference of the hyperverse is equal to 2 pi times 2c, and we'll divide that by the circumference of the hyperverse, which is 2 pi times its radius of the hyperverse. And the 2 pi cancels out, and we find that we get 2c divided by r sub h. And the answer, 2c over r sub h, is the Hubble constant. The Hubble constant is a measure of the rate that galaxies separate from one another. The most recent measurement from the Planck mission is about 67.8 kilometers per second per megaparsec of separation. If we convert megaparsecs to kilometers for easy comparison, we take our Planck mission value of 67.8 kilometers per second per megaparsec, but convert that to kilometers, and we get a value for the Hubble constant of about 2.197 times 10 to the minus 18th per second. You notice the distances cancel out. Our value for the Hubble constant, 2c over r sub h, comes to 2.173 times 10 to the minus 18th per second. You find these numbers are almost spot on. Matching the Hubble constant is a significant result. The balloon analogy, so often used in cosmology, may represent the actual structure of the universe. If the universe were the surface volume of a 4D hypersphere, we find the radial into the fourth dimension expansion is twice the speed of light. The circumferential expansion matches the Hubble constant. And this is in addition to a surface of a 4D sphere giving us a positively curved, finite, enclosed space, as favored in modern cosmology. And with the hyperverse concept, the universe is its surface. That is, the universe is the surface volume of a 4D sphere, the hyperverse. This explains why the universe appears to have no center and no edge. The center is in the center of the hypersphere, in the past. It does not reside on the surface in the universe. The edge of space is not at some far-off location. It is everywhere. Every point in space is at the edge of space. You, I, everything, everywhere is at the edge of space. And since every point in space is on the surface of the hyperverse, every point in space is moving radially into the fourth dimension at twice the speed of light. All this makes it appear that the universe is indeed the three-dimensional surface of a hollow, expanding 4D hypersphere or hyperverse. And let us briefly look at some what I hope are immediate consequences or thoughts you may have about this concept. If the universe is expanding radially at twice the speed of light, you might ask yourself, how do you experience this 2c radial expansion? How about time? The cosmological arrow of time points one way, in the direction that space is expanding. Nobody ever tells you which way that is, though. The hyperverse model gives us that direction, into the fourth dimension. We will make the claim elsewhere that the 2c radial expansion of space is the foundation of time. The 2c radial expansion immediately suggests a reason that nothing in the universe can move faster than the speed of light. The speed of light is limited to 1/2 of the radial expansion rate. If the universe is the three-dimensional surface volume of a 4D hypersphere, the surface will have a thickness in the fourth dimension. What do you think might happen to the thickness of the hyperverse surface with expansion? That last topic we will discuss in detail in the paper and videos on the geometric mean expansion of space. What we have in this video is just the beginning. The concepts are explained further in other videos and papers located at jimtasano.com. Thank you.